CXL 3.0 protocol training. First, let us start off with the understanding training schedule. It will be run for 6 weeks. It's a 6 weeks program. We'll be doing the training over the weekend, Saturday and Sunday, around 3.5 hours per day. That will be from 10 a.m. to 1:30 p.m. There is a possibility that we might move this schedule to 9 a.m. to 12:30 p.m. if majority of people are you're fine, because there are some participants from US and outside of India who have requested me to change the timing bit early so that they can also attend the live sessions. So okay. That is where plus or minus 1 hour possibility is there, and typically it would, including the breaks and everything, it would go for 36 hours of teaching overall. As part of this training, for every topic that we cover in a week, we'll provide assignments specific to those topics covered in each week, and we will also provide you with the interview questions. Mostly this assignment specific topics will become the interview questions, and this course is only a protocol focused training. It doesn't cover any coding or any test bench development. The protocol will be covered from the very basics of CXL. You see, CXL is not something that is invented from developed from scratch. See, it uses a lot of concepts from other protocols, like it could be PCI Express, it could be coherency protocols like ACE protocol. So there are many things it takes from different protocols. So we need to understand those basics before we really learn the advanced aspects of CXL 3.2. So basically this will be targeting all categories of the audience. So I don't assume that you are already familiar with CXL 1.2 or CXL 2.2 and you are learning CXL 3.2. So I will assume that most of you don't have much exposure to the CXL. So I would start from the very basics. That is where we are spending 36 plus hours. If you are already good with PCI Express, if you are already good with cache coherency, it can all be finished in 15 to 20 hours. But since we start from the basics, we will cover all the aspects of coherence, all the aspects of whatever is relevant aspects of PCI. So this training would go for around 36 plus hours. Now, what are the course prerequisites? You need a good understanding of PCI protocol basics. You don't need to be expert with physical layer. You don't need to be expert with very in-depth of PCI, but at least at top level, you should have a good understanding about what all layers are there, how the enumeration happens, what is significance of transaction layer, what is significance of data link layer, physical layer. That level of understanding you should have. You should also have an understanding of what is TLP, what is DLLP, what is order set. That much basic understanding is required for this course. We may touch upon some basics, but I would suggest if you are enrolling for CXL course, you should spend some time revising the PCI Express. Other than that, you should also have some basics of cache coherency, but as I said, I don't expect you to come with all this with a good understanding of this. I will cover all these things from the scratch, cache coherency basics also, because the CXL at one point is majorly about coherency. I mean, because it's more about sharing the pool of memories across the connected devices into the interconnect. So how do we maintain coherency across all these shared memories is what is essence of CXL. So we'll be touching upon the cache coherency there. Then we'll also need to understand memory basics. I mean, because we are talking about CXL is all about expansion of memory. I mean, the type 3 devices in CXL is about expansion of memory and then cache coherency. So one aspect of CXL is cache coherency. The other aspect of CXL is the memory expansion. So you need to understand how does memory work in an SOC. If I take an SOC, what is the significance of a cache? What is significance of a DDR or a system memory? What is significance of other secondary storage memories? So all that we will be also touching upon. Then I would suggest you to fill this form. I mean, you don't need to fill it immediately. I have sent it to your email ID. What is this form is basically, I'm trying to understand what is your current understanding. Let's say there are around 25 participants in this meeting. So I want, or 35 participants, I want to know your current expertise level with these basics. I mean, do you know PCI Express protocol? Do you know cache coherency concepts? Are you familiar with memory basics? So those kind of things I want to know. You must have got this email with this link to your email ID. Please fill this form by end of the day so that I understand what is the category distribution of the participants. Accordingly, I can structure the course from tomorrow onwards. If everyone is good with the basic, I could directly start with the advanced topics. Everyone, please be in mute. Shivanshu Rana, please be in mute. Okay, what is the agenda? Agenda is basically we will try to cover pretty much everything of the CXL because I wanted it to be one comprehensive course which covers all the aspects, not just the type 1, type 2, type 3 devices, not just the interconnect concepts, touch upon all the layers, the link layer, the transaction layer, the link layer, the physical layer, uh, the packet format, different types of transactions generated in the cache semantics, different types of transaction generated in the mem semantics. So there are a lot of things. So we will touch upon all those things as we go forward. So this would be the agenda. So initially we will start off with the CXL overview and how CXL has evolved over the time. I mean, it's a very recent protocol. It all started in 2019. So in 4 years, it has made a lot of progress. How do we say a lot of progress is it has got around 100 plus companies who are part of the CXL consortium. I mean, these are 100 plus companies are the one who gives the input and who are interested in CXL. I mean, you can understand in 4 years, so many companies have joined into CXL. That means you can imagine how many products will come out into the market with CXL based implementation. Because let's say Micron is joining into that CXL consortium. So they wouldn't just join, right, for without having any interest. They're joining because they're going to come out with the products based on CXL. Let's say Intel is the one who has actually initiated this whole thing. So Intel has already come out with the products which are based on CXL. Let's say AMD has joined. So they will also have some interest because they work into server market. So servers and all that would be essentially using the CXL going forward. Okay. So essentially CXL is the next generation interconnect for the data centers. There are many other uh, protocols like Gen-G. There are another 3, 4 are there, but CXL has definitely taken the significant lead over all other protocols. Next. We will also be touching upon what is the need for a CXL. When we have so many protocols, PCI Express, UFS, UCIe, so many protocols are already there. Why do we really require one more new protocol called as CXL? Then we'll also touch upon what basics we need to learn before CXL, because we cannot directly jump into what is link layer, what is transaction layer, what is a fleet, what is cache transaction, memory transaction. There are some basics we need to learn before we go into CXL. So we'll touch upon those basics also. That will make it easy for you to understand the CXL protocol. Next, we'll be touching upon feature summary. I mean, how the things has evolved starting from 1.0, 1.1, 2.0. Now we are in 3.0 generation of the CXL. So what new features got added with each generation we'll talk about. And then CXL has three protocols. One is IO protocol, one is cache protocol, one is mem protocol. So we'll touch upon all these protocols. Then we'll be touching upon the system architecture. I mean, how does a CXL based system architecture looks like? I mean, when we say there are different types of devices, type 1, type 2, and type 3 devices, what are those exactly, and why those devices are, what is the applications for which these devices are targeted for? As we go forward, you'll understand that type 1 and type 2 are mostly targeted for accelerator kind of applications where they are specially designed hardware to complete a work quickly. I mean, it's like a DSP processor, which is specially designed for processing the mathematical equations, those kind of things. Type 3 devices will be used for memory expansion purpose. We will also talk about why we need to do memory expansion in systems. I mean, what is the need to do with so much DDR memory, so much SSD memory? Why do you require memory expansion? So we'll talk about all that. Then we'll also talk about what is the concept of multi-logical device, CXL device scaling, the how CXL fabric looks like. Then there is a concept called as GFAM type 3 device. We'll talk about that. This relates to pooling of a memory at one place and just sharing across the entire topology. Then we'll be touching upon the individual layers of the CXL, that is transaction layer, where we'll talk about IO, cache, and mem specific aspects of the transaction layer. Then we'll talk about transaction ordering summary and how transaction flows to device attached memory. Then we'll talk about CXL link layer with respect to IO, with respect to cache and mem. Then we'll talk about what is a flit. See, if you are familiar with PCI Express till Gen 5, we used to talk in terms of the TLP packets and all that. The basic unit used to be a packet. I mean, it used to be 128 bit converted into 130 bit. Okay, this is still Gen 5. Gen 6, we don't do this. It's a 1 bit by 1 bit encoding only. We use something called as flit there. So the size of the flit is 256 bytes. The same thing they use in the CXL because CXL is completely inherited from PCI Express. I mean, everything you do in CXL is built on top of PCI Express because they didn't want to invent something again from scratch. They didn't want to reinvent the wheel. They wanted to use the existing infrastructure, existing technology, and build on top of that. That is where they use the Gen 6 concepts to build CXL, Gen 5 and Gen 6 concepts. Okay. Other than that, CXL also has arbitrator and multiplexing logic because these are required because there are packets coming from IO, cache, and mem blocks in different types of devices. To arbitrate them, we need a arbitrator and multiplexing logic. Then we'll also talk about the physical layer, that is called as flex bus physical layer. So we'll talk about what is this 256 byte flit, 68 byte flit, what is how the link training happens, everything we'll talk about. Then we'll be talking about switching concepts, how the switch configuration happens. I mean, this switching is similar to what we are talking about, the switches in the PCI Express. You know, right? What does switch do? You have got one upstream port and multiple downstream port. So the switch is used to connect one upstream port going to the root to the multiple downstream port with other devices connected. Same is the concept of switching in CXL also. So we'll touch upon all those concepts. How does that switch and fabric architecture looks like, everything. Then we'll be talking about control and status registers associated with the CXL, that is configuration space registers and memory mapped register. Then we'll be talking about the reset, initialization, configuration, and manageability, all the concepts with respect to these topics. Then we'll also talk about power management. What is CXL power management and how the link power management works by using CXL.io. Okay. Then we'll also talk about some basics of security. We may not go deep into it, but we'll talk about security. Then we'll talk about some reliability. This is called as RAS, right? RAS, reliability, availability, and serviceability is a very important aspect of every system. So we'll talk about all that. Then some performance considerations also we'll talk about. So this is the agenda in brief. I know that you probably didn't understood. I mean, don't remember all of this, but as we go forward, we will explain all these topics in detail. Okay. Now let us start off with the CXL overview. What exactly is a CXL? CXL stands for Compute Express Link. It is a CXL is a high-speed interconnect. Basically, it's an interconnect technology. It's an industry standard interface. Why is it industry standard? With so many companies joining into the CXL consortium, everyone has taken this as a standard for high-speed interconnect implementations. This is an interface used for communication between the processor, accelerators like GPUs, and memory and storage and other IO devices. You see, you can connect so many things into the CXL interconnect. One is you can connect processor cores, accelerators, memory, the storage, and the other IO devices. CXL is a dynamic multi-protocol technology. What is meant by multi-protocol is it supports IO technology, IO protocol, cache protocol, memory protocol, all embedded into just one protocol called CXL. What is dynamic is they all can be multiplexed. I mean, it's not like CXL will only work in IO mode or it will only work in MEM mode. You can just use any of that dynamically at the runtime. These are designed to support accelerator and memory devices. I told you, right? Some type of target is accelerators, in some other applications, the target is memory devices. Then CXL provides a low latency. Latency is a very important topic here. I will explain you how we get low latency. Essentially, in one word summary, we get low latency because we use PCI Express Gen 6, which works at 64 gigatransfers per second. That is where you get very less latency. High bandwidth path for an accelerator to access the system, and for system to access the memory attached to the CXL device. I mean, because everything is connected to a very high speed interconnect. For anything to access anything else, it will be possible with low latency and high bandwidth. Next. So any questions you have till this point? Now let us understand how the CXL has evolved. CXL has evolved in 3 revisions. One is CXL 1.0, which was released in March 2019. It was actually initiated by the Intel. Basically, what CXL 1.0 does is it allows for expanding of system memory through the CXL interconnect. What is system memory is generally in majority of cases we refer to DDR as the system memory. Okay, with CXL technology, CXL protocol and CXL interconnect based thing, your system memory doesn't limit to just DDR. You can use just any memory to work as a system memory. That is because the CXL will take care of the latency and the bandwidth. So earlier, without CXL, the problem was DDR used to be the one which used to fulfill all that system requirements. I mean, high low latency, high bandwidth requirement. Then what they did is, see, DDR was becoming a limitation. So the amount of DDR that you can have in a system was becoming a limitation. To address that, they introduced CXL interconnect, where you can connect your memory device, and if, let's say if the core is sitting here, it can access this information with very minimal latency with very high bandwidth. That is what CXL interconnect does. This is what I'm talking as a CXL interconnect. That was a very basic thing that was done in CXL 1.0. Then what they did in CXL 1.1, it still has single node connection. This was released in December 2019, which was very much 7-8 months after this one. It's a single node connection with no provision for the switches. In CXL 2.0, that is released in October 2020, they introduced the concept of memory pooling. What is memory pooling is, you can share the memory across multiple cores. It's not like a one-to-one mapping that this memory is reserved for this processor, other memory is reserved for other processor. It's not like that. You could pool the memory, and one processor could access the resources from two different memories. Let's say there is this memory. This is my processor. It could use the resource, the memory space from here. It could also use the memory space from here. So that way what it became is, it increased the efficiency of the memory utilization. But then the other catch is, you cannot have some other device writing into this. That was the problem with CXL 2.0, because this is kind of reserved for this one. Okay, this is reserved for this one. When CXL 3.0, they have addressed that issue also, because they have introduced some concept called as enhanced cache coherency in CXL 3.0, which introduced a concept called as back invalidation. What is back invalidation? What is cache? Everything I'll touch upon. Through that, it became possible where same memory segments could be accessed by multiple memories in a coherent manner. Okay. So CXL 2.0 introduced the concept of memory pooling and the concept of CXL switches. What does CXL switches will do is, it allows for multiple devices to be connected. So you just don't have to do one connection. You could connect many devices into the topology through the switches. Then this was still not very big thing, because it was still a limiting, because what this will do is, and the problem was, it was only one level of switching. You cannot do multi-level switching. That was a big limitation, because you could connect only few tens of devices into the topology. You could connect processors, few tens of other accelerators and devices. That was a limitation in the current requirements. In the current requirements, yeah, the current requirements, we are talking about connecting hundreds of cores, hundreds of memories into the topology. That is what they have done in CXL 3.0. What they have done in CXL 3.0 is, which is released in 2022 August. First thing they did is they doubled the per lane throughput to 64 gigatransfers per second. So how did they double? I mean, earlier it was 32 gigatransfers per second. In CXL 3.0, they doubled it to 64. What they did is the CXL 2.0 was working on PCIe Gen 5. Okay, then they moved to Gen 6 in CXL 3.0. That without doing any effort, see, CXL consortium, without taking any new effort or any additional effort, they were just able to double the throughput. No latency addition, no additional protocols need to be introduced. They just had to use the Gen 6 as the base standard for implementing 3.0. That is one major thing they have done, because doubling of a frequency is a really big thing. I mean, probably we don't notice it, but if you look from a data center perspective, what would take 1 minute, let's say if it finished in 30 seconds, the same activity, it's a big thing actually. And that too at no additional cost actually. I mean, no big overhead or no big latency overhead. The next thing, the PCI Express Gen 6 introduces a concept called as forward error correction, and till CXL 2.0, the flit size used to be, flit is like a fixed packet, the size of a packet that will be used for transmission purpose. That is what we call as flit going forward. The flit size is increased from 250 to 256 bytes. In 2.0, it used to be 68 bytes. It used to be 68 bytes, that they have increased it to 256 bytes. Now, what is this has done is, it gave provision for increasing the header size. I will talk about all those things in the later slides. The most important, very important enhancement that happened in CXL 3.0 is the enhanced coherency. See, CXL 2.0 inherently had a concept called as cache coherency, where all the caches will be coherent with respect to the system memory. With CXL 3.0, they introduced the concept of cache coherency, which comes with a concept called as back invalidation, which allows for device to tell to the core that this location, my location has changed. Since it has changed, you invalidate your location. Let's say you have cached, let's say I'm talking about my location as address equal to 100. If my in the device some data has changed that address equal to 100, so there is a provision through the back invalidation where my device can tell to the processor that location at 100 has changed. If you have cached this location 100 in your cache, invalidate it. That concept is called as enhanced coherency or back invalidation. That is a very powerful thing, because that allows all the cores to be incoherent with the device memory also. We'll talk more of that as we go forward. Other than that, memory pooling and sharing became more effective now because of back invalidation. There is a complete coherency in the system, so the pooling and sharing becomes very easy because of that. And multi-level topologies are there. If you remember in CXL 2.0, I told that it only support one level of switch. That means if there is one device, you can only have one switch. Below that, you cannot have next level of switch. You cannot connect a device here. This is not possible, because this will become two-tier switching. Whereas in 3.0, this multi-tier switching is possible. Multi-level topologies are possible. That is also a big update, because that gives a lot of flexibility to create different type of connection topologies. So you might be aware, right? If you have gone through some basics of Ethernet, network can be connected in ring topology. There are different some 5-6 different types of topologies are there. This multi-level topology gives me provision to create whatever type of topology I need. With one level of topology, it's not possible. Okay, one level of topology means you just have to rely as a star topology only. Whereas with multi levels, you can do lot of uh, combinations of topology connections. Other than that, what are the new other updates that happened in CXL 3.0? As I said, this will give provision for multi-level switching. Then, because of this memory pooling and sharing, and because of this back invalidation, more importantly, due to this enhanced coherency concept, peer-to-peer connectivity between devices also becomes possible. I mean, without the intervention of the processor, one device which is connected on the CXL interconnect can write and read into the other device memory without intervention from the switch or from the processor. What does it do is it makes sure that uh, processor bandwidth is not consumed. Understand, right? If peer can directly talk to a peer without involving the processor, it reduces the core interference. I mean, the core bandwidth can be used for something else. When I say core, I'm talking about a processor. Okay. We'll talk more about this as we go forward. I mean, this I'm just listing down the summary of changes that happened in CXL 3.0. Other than that, multiple devices of type 1, type 2, type 3 can be connected per root port. See, in CXL 2.0, there was a limitation. Either you can connect type 1 or one type 2. That's all. You can connect multiple type 3 in CXL 2.0. We could only connect below a root port. We could connect only either type 1 or type 2. Only one device. And multiple type 3 was possible. But with CXL 3.0, that whole restriction is not there. I mean, we can connect any number of type 1, 2, 3 devices below the root port. When I say root port, I'm talking about the port that is coming from the root complex level. If you remember PCI Express, you know the topology, right? We have a root complex, below that the entire topology will be there. So because there is no such restriction, now the overall architecture becomes very flexible. You can connect any number of accelerators, you can connect any number of memory expansion. So that makes the I mean, you can get so much performance and so much memory expansion out of this CXL 3.0 architecture. Then it introduces a concept called as a GFAM, which stands for Global Fabric Attached Memory. See, as I said, it's a common memory. I mean, it's a memory that can be shared across the fabric. That concept is also introduced. So you see, there are so many new things happen in CXL 3.0. That is why 3.0 is will be the next big thing in the overall interconnect market. Now, let us start off with understanding why do we need a CXL? I mean, with so many, as I told you before, with so many protocols like PCI Express, UCIe, UFS, and many other protocols, right? On-chip protocols. Why do you need a new protocol? So let's try to understand this. First thing is I mean, this can be summarized into two statements. One is the memory wall problem. This, if you search memory wall problem in the internet, you will get it. It's a keyword in itself. Memory wall is it's one of the keywords in the industry. Okay. The second is the IT resource efficiency maximization. How can we efficiently utilize the resources? Like when I say resources, I'm talking about the memories, accelerators, the processors, everything. How can we efficiently utilize them? Okay. So the first thing is uh, changing industry landscape. Mean, you see, we had a concept of cloud computing for last 10-15 years. I mean, we used to hear cloud computing, hosting on a cloud, everything for last 10 years at least. Even we used to hear about artificial intelligence and analytics for last 10-15 years. And we are talking about hosting everything, network, and doing edge computing, cloudification of network and edge computing. But the things, what is happening is, with the evolution of all this new type of artificial intelligence and data science and everything, uh, it has become more intensive. I mean, the things have become more resource hungry. I mean, the all the applications require a lot of computing hardware, computing resources. That is where you need a technology which gives that flexibility. So that is one reason why CXL was developed. So the need to process and analyze large data set generated by the cloud application. So you generate, when you do artificial intelligence and all that, it generates a lot of data that need to be analyzed by the application. So that is where you need CXL kind of interconnects. Then uh, CXL offers a low latency interconnect. I mean, it does all these things powerfully at very low latency. So we'll also discuss where do we get this, I mean, how do we achieve low latency while we are getting all these benefits. We'll talk about all those things. One line answer will be, answer is PCI Express Gen 6 is the answer for that. Basically, you take the power of Gen 6 and build everything on top of that. Next. First, let's understand what exactly is the memory wall problem. Can someone tell me what do you understand from the term memory wall problem?
Memory pooling is not is a big issue. Sharing of memory across the
Uh,
devices.
yeah, sharing of the memory is correct, but more importantly, when we say wall, let's understand what exactly does it mean. What you said is correct, but it doesn't directly refer to memory wall. We'll talk about that. Okay, if you understand the, I mean, let us start off with understanding some basics of the system memory in the SoC. Let's say my laptop is there. In my laptop, can you tell me what can I call as a system memory? What all things in my laptop can I call them as system memories?
Your RAM, basically your
RAM,
DDR, and
DDR, okay,
yeah, and the
even
and the cache.
ROM, cache, even flash, which is attached to the processor. These all things I can call as a system memory. What is the importance of system memory? I mean, why do we need? Let's say, can my laptop run without DDR? Tell me. Imagine my laptop. I have a 1 terabyte SSD, 1 terabyte SSD, but no DDR. Will my system run?
No, no,
What problem will
it
I
need
face?
uh like it needs to store the processes in the RAM before caching them into the cache itself. So like it needs the processes, they need to be allocated somewhere in a faster memory. Hard disk is too slow for CPU to get the data.
Yeah, thank you so much for that inputs. See, basically, if you understand the diagram you see in the down will summarize what Shivanshu has said. Okay, basically, my CPU has a associated cache memory, uh, and it also can interface with RAM. The CPU never interfaces to the hard disk. I mean, if you take my let's say Intel core is there. I have i5 core, for example. That will never talk to hard disk directly. It could be SSD, it could be HDD. It will never talk to these devices directly. It always interfaces to the system memory. System memory in turn interfaces to the hard disk. Then there will be a mechanism of DMA, direct memory access, through which these applications and data that is present in this one will be moved into DDR. So in summary, the system memory is the interface through which CPU sees the entire memory space. I mean, you may have 1 terabyte hard disk, but CPU doesn't see 1 terabyte hard disk. CPU sees only the system memory that you have got. Most of the time, the system memory happens to be the DDR. So if your DDR is 4 gigabyte DDR, so for your CPU, 4 gigabyte is the only memory, actually speaking. Now you may say 1 terabyte is also there, but for CPU it doesn't bother. Uh, it is the DMA which transfers that data here, then CPU will access it. So that is the importance of system memory in the SoC. Now, like the other person Shivanshu was telling, like whatever applications you open, like for example, I have opened here PowerPoint. I'm running my this online meeting. All this application code. See, these all applications are at the end of the day they are instructions, right? Intel specific instructions, CISC instructions. All these are loaded into my DDR memory inside my laptop, and my Intel i5 core is fetching those instructions and is executing. That is how these applications are running. They won't be actually, to start with, all these applications are present here. See, when you turn off my laptop, let's say this is my laptop, I power it off. What will happen? The entire RAM data will get lost, entire cache memory data will be lost. Where is the data actually present? It is present in the hard disk. When you turn on your laptop during the boot up, page tables will get created, which as part of that, the data will, essential applications and whatever applications you open, they will get moved here. And if this is a hard fast memory, the movement will be quicker. If it is a hard disk drive which is slow, the movement will be slower. That is where you will see that when you boot up your laptop, if it is based on SSD device, the boot up will be fast, otherwise boot will be slower, because this one, if it is HDD hard disk drive, it will give the data slowly. Okay, now once you have once you have loaded your applications here, my CPU only talks to the DDR, it doesn't talk to hard disk. That is where the amount of memory that you reserve, keep for DDR, system memory, is very important for how many applications you can run and how quickly those applications will be run. So basically, in summary, how many applications we can run and how quickly they will run is a direct function of system memory size and speed. See, system memory also works at a specific speed, right? If you see, DDR4 works at specific speed. DDR5 works at a even bigger, better speed compared to DDR4. So if you are using DDR5, you will get a better performance because it will be having a bigger size and bigger speed. Hence, my processor will get the data quickly. So in summary, it is a direct function of the system memory. How quick is my overall system? With this understanding, let us quickly read through this slide. Okay, see, SOC use cases involve access to the memory. Anything you do in SOC, for example, I'm doing a presentation, I'm transferring one data from my laptop to pen drive. Anything I do, even when I'm running online meeting, it is all about data processing. It is all about moving data from one part of the chip to another part of the chip. So it's all about access to the memory. SOC applications are all about high bandwidth and low latency. So if you want better performance, you want high bandwidth, and it should happen with a low latency. It requires processor access to the memory with minimal latency.
Excuse me, Srinivas. Uh,
Yeah.
uh, can the screen size be a little bigger?
No, no, you have a provision to make it bigger. I mean, when you go in your application, right? Go to meeting where you open. You have to, in the top middle top of your screen, there will be a provision to do that. Actually,
I have camera activation and then settings.
I think
I
camera
have joined through
activation there
browser
means
actually. I have joined through browser. Okay, okay,
there
toggle
will
full
be,
screen. Okay, okay,
yeah.
yeah, yeah, got it. Okay, okay, yeah. Thank you.
Okay. So as I said, it requires processor access to the memory with minimal latency. Okay. Then initially when system boots, as I said, please be in mute, everyone. Please be in mute. So initially when the system boots up, cache doesn't have any data. RAM doesn't have any data. Everything is present in the hard disk. All this application, all the data and applications, everything is present in HDD or SSD. So the applications and instruction, application means instructions, and the data could be what my I have a movie file which need to be played. That is the data. The application means the VLC player. In case of movie, VLC player is the application, data is the movie file. So both of them are present in the these things only, HDD or SSD. Initially when you boot up, what will happen is the page tables are loaded, application code is moved to DDR by means of a DMA transfers. DDR is the system memory, or also called as primary memory, that is directly accessible by the CPU. it provides actual working space to the processor. I mean, the amount of DDR limits is what is the working space of the processor. Next, HDD, SSD are secondary memories. They are not the primary memories. These are secondary memories whose data first gets transferred to primary memory by means of DMA, then accessed by the processor. Processor doesn't directly access the secondary memory contents. Okay. So this is a brief about what is the significance of system memory in the SoC. So in summary, what I'm trying to tell is, larger this memory, the better will be the system performance. Now, why we are talking about this is, in the latest generations of the data centers, the cloud infrastructure, what is happening is number of cores are getting increased. See, the number of cores are increasing significantly, but the RAM size is not increasing in the same proportion. That means if you are increasing CPU from 1 to 100, let's say initially for one you had 4 GB RAM, this should ideally become 400 GB of RAM. That is not happening. So there we are hitting a limitation where the amount of RAM that corresponds to per CPU is not catching up with the number of CPU cores or number of processing units. Please be in mute. Everyone, please be in mute. See, I mean, you don't notice NK, someone by NK, there is a noise. Everyone feels the disturbance. Next, let us understand what exactly is a data center, because primarily CXL is targeted for data centers and cloud infrastructure. So what exactly is a data center? Can someone tell me what all things are part of a data center? When I say data center, what do you think of it?
It should have multiple processor cores. It should have a lot of shared memory. It should have a mean to connect to the internet, basically a really high-speed internet connection, and a lot of storage as well. Or it could depend
Essentially,
on it could also depend on the nature of the data center. So basically, the application it is used for. So if it is getting used for specifically, let's say uh, maybe the AI task, then the GPU will be more prominent in this type of data center as opposed to having more CPUs. CPUs will be
yeah,
used
yeah.
only for
So
distribution of the workload, things like that. Yeah.
yeah, exactly. Thank you so much. It very much summarizes what a data center is. Basically, it's all about mixing of all these things in the right proportion, like number of cores, the amount of memory, amount of accelerators, and the switches, routers, everything, and connection to the high-speed internet. Everything is what makes the data center. Data center is where all the important applications of any company are run on. Okay. Uh, a data center is basically a physical facility that organizations use to house their critical applications and the data. Their applications and data will also be present. It's not just the application, it's the data also will be present here. For example, let's take our training institute. We have tools from the various companies, let's say Mentor and Synopsys. We host them on cloud, for example. So all our applications like Synopsys tools and the Mentor tools and all other company, as any other specific company tools are installed into the cloud, and the corresponding data related to all these projects is all hosted into the data center. When one of my student wants to access this data, so he wants it to be accessed at a very high bandwidth and with minimum latency. It should not be happening with some delay in the speed at which he accesses. That is where the number of cores you have got, the amount of RAM, amount of the system memory, the amount of storage for data, everything becomes very important in the data center. The key components of data center design includes, what is the data center includes? Basically the routers, the switches, the firewalls make sure that it will be protected, the access will be protected to the required users only, the storage systems, the servers, and the application delivery controllers. So this part is what CXL majorly targets at. the storage system and the servers and the accelerators. Though one thing we are missing here is accelerators. Accelerators are also part of a data center. What is an accelerator is, it's a specially designed circuit to handle some applications in a quick manner. Let's say my ARM processor is there. Okay. Then there is a one DSP processor. I want to do some mathematical equations. I want to solve some mathematical equation. Even though ARM is a powerful processor, it is not good for that. It is not meant for that. So the DSP processor is meant for that. So these kind of special hardware, which is meant to handle some special application, they will be called as accelerator. Even you see accelerators require a quick access to the data because they do a lot of processing. So that is where we need a high bandwidth and low latency connection. I mean, that is the keyword I will keep using because CXL is all about that same thing, high bandwidth and low latency interconnect. Next, what is the current limitations with the data centers? I mean, we understood what exactly is a data center. Now let us understand what are the limitations with the data centers. Data centers, as you know, consists of large number of servers. Everything you see here was a server. I mean, this all could be the storage system, servers, everything is collectively what you see here is. Okay. As I said, data centers consists of large number of servers. What exactly is a server? Large number of processor cores connected to large amount of DDR is what in summary makes the server. It is all about high performance at low latency with large storage. You want very high performance with low latency and with large amount of storage space. All of this requires, if you understand, high performance again comes through the speed at which memory can be accessed. Low latency again comes from the frequency, how quickly the memory will respond with the data, and the large storage is again related to the memory only. So it's all about having a lot of high performance memory. Okay. These cores are running lot of user applications in parallel. You see, if I talk about our institute, whole setup is hosted on the cloud. There could be many users who could be running different applications concurrently. This requires a lot of system memory because each of their applications are running in the system memory. So each, let's assume, takes some gigabytes of data. So with many users, it will require a lot of system memory. If it is only my laptop, I'm the only person using, so the limited DDR would be sufficient. But if it is a server or a data center with many people parallelly running the applications, each application will take its own data, so it will require a large amount of system memory. So when I say system memory, we are talking about either DDR, flash, ROM, or cache. These all will fall under system memory. Among all these, DDR is the best option, which gives optimal performance, optimal cost, and optimal area. See, cache gives you very high performance, but the cost is very high, area is very high. DDR is something where it falls in the right place, where you get a very good performance at a low cost and relatively low area. Now, server motherboards, if you look at the statistics in the following slides, you will understand that server motherboards are limited by the number of DDR channels. I mean, how many DDR channels you have in the motherboard is what limits the your amount of DDR that you can connect. I mean, what do I mean by that is, if you open your desktop or laptop anytime, let's say you happen to open anytime, you will notice that your motherboard will have generally two slots of DDR. I mean, where you can insert DDR. Okay. Now, this is the limit. You cannot insert more DDRs than this. Now, what is that you can insert here also gets limited, right? You cannot insert 1 terabyte of DDR. You cannot insert hundreds of gigabytes of DDR because each DDR is a DIMM, dual inline memory module. This itself comes with some specific capacity. But the same system can have a processor with 32 cores. Let's say I'm talking about servers. I can have 32 cores. Imagine I have got a 64 gigabytes of RAM. My RAM is 64 gigabyte. My core is 32 cores. So how much RAM do I have for each core? 64 gigabyte divided by 32. That means imagine a system where you have got a server with 32 cores having 64 gigabyte of DDR core or DDR5, let it be. So per core, the RAM will be, DDR will be 64 gigabyte by 32. So it will be 2 gigabyte. It's on a much lower side. I mean, imagine if, because 32 cores are there, 32 concurrent users could be running application, concurrent applications could be running, right? Because if there are 32 cores, they can run 32 concurrent applications. So each application gets only 2 gigabyte of workable area. Workable area means what? The system memory. Now you may say, how about connecting 128 gigabyte? It is possible. It is possible. But beyond that, it becomes difficult because the amount of DDR system memory or DDR we can connect into motherboard. We can connect to into motherboard is limited by number of channels. Which limits the amount of the DDR connected. So what is a possible solution for this? I mean, how do we solve this problem? One is accommodate more DIMMs per channel. If you understand the DDR technology, you will know that in one channel you can have multiple DIMMs also. It is possible where you can have some selection to select among the multiple DIMMs, whichever DIMM you want access. But then the problem is, as you keep increasing the DIMMs, it limits the frequency of operation due to increased load. See, when you connect multiple DIMMs, that all things becomes a load on the channel, right? Per channel load will increase. That will reduce the frequency of operation. That will increase the latency. So when you try to add more DIMMs, it will impact the frequency of operation. Okay. So in summary, data centers are current limitation with data centers are limited by the amount of DDR that can be connected into the system. Any questions in this slide? Next. Okay. What exactly is the primary storage or system memory? Let's quickly walk through it. Primary storage or system memory holds the data, holds the programs and instructions that are currently in use. They are located on the motherboard. As a result, data can be read from or and written to primary storage extremely quickly because they are directly connected on the located on the motherboard. You see, even your DDR is directly located on the DDR, so the latency of access will be very less. This gives the processor fast access to the data and instruction that primary storage holds. There are 4 types of primary storage: read-only memory, ROM, random access memory, flash, and cache memory. DDR offers the optimal solution among all these. Next, system memory in SoC architecture. See, DDR is used as a system memory. In this, going forward, you'll understand that when you talk from a DDR and cache perspective, the unit of data transfer between cache and DDR is called as cache line. We'll understand that. We'll use a term called as cache line. That is the basic unit of transfer between the cache and the DDR. So how do you understand that? If this is my processor subsystem, it has got multiple cores. Each core has a L1 cache, and associated with the entire processor subsystem, I have L2 cache. Then I've got a system memory, that is the DDR. Then I have got HDD SSD. There is a possibility where my core can directly access the DDR. That is called as non-cacheable locations. Some locations they don't need to be part of cache. So those non-cacheable addresses, my core will directly access by skipping L1 and L2 cache. For then there are other type of locations which need to be cached. So they will be allocated into L1 cache, L2 cache. So the access will happen through L1 and L2 cache. You should understand that L1 is closest to the core, so the latency will be very minimal. I mean, if a core issues a read to the L1 cache, it may get the response very much within 15 nanoseconds time. Let's say L2 cache may take 20 nanoseconds time. The DDR may take around 60 nanoseconds time. I mean, in talking in a real terms, I mean, in real life also, these numbers will hold good. Okay. So as you go from L1 to L2, L2 to DDR, the amount of time it takes to load the application will be bigger. When we are talking about, let's say that there is a page fault where that application is not present here, you have to fetch from here. That will add up to another 300 nanoseconds. This will be slower actually. Anything related to SSD and HDD access will be slower. See, SSD may give you 300, HDD may give you 1000 nanoseconds, because that is even more slower. So here we need to understand the importance of L1 and L2 cache. This understanding is important because this is the primary thing. It drives one half of the CXL. See, one half of the CXL is about cache coherency. So understanding what is L1 cache, what is L2 cache, what is the significance of a cache in a system is very important. See, what does cache hold is, cache uh, holds the information of data of frequently accessed locations, address locations. It could be the applications if we are talking about. Now, since they are being frequently accessed, you want that to be accessed with a minimum latency. So if you hold the information in L1 cache or L2 cache, the access will be much quicker. Rather, if you have to get it from DDR, it will be slower because we are talking about around 60 nanoseconds latency. If you have to get the same thing from HDD or SSD, it will be even slower. So the processor systems introduces a concept called as L1 cache and L2 cache, which makes the application access latency much lower. Okay. I hope you got a basic idea about where does L1 cache fit into the architecture, where does L2 cache, where does DDR and STD, SSD fit into the architecture. Next, different memory categories. There will be two types of memories: volatile memories, non-volatile memories. Cache and RAM is a non-volatile, sorry, volatile in nature. What is volatile is, once you turn off the power, they both lose the information, whereas hard disk doesn't lose the information. Uh, okay. Cache memory, main memory, that is the system memory or the DDR. All the applications and page tables are created here. Core only accesses the main memory. What is non-volatile memory? It could be SSD or HDD or magnetic tapes. That is the user data and application data will be present here. All that we have discussed. Uh, One thing you need to understand is, as you go up, mean from HDD to SSD, SSD to DDR, DDR to cache, the access time will decrease. I mean, the amount of time it takes to access the memory will be less. Cost also increases. Okay, these are all the things which are driving the industry for a alternate solutions. See, you could use 256 gigabyte of DDR, but the amount of cost you have to spend will be very high. See, that is practically the problem even we are facing as an institute. For example, we have multiple servers. When I'm placing an order, as I increase, they are giving me DDR with 64 gigabyte configuration. Let's say they are quoting me 4.5 lakhs. Okay, when I'm asking, give me 128 gigabyte configuration, it suddenly jumps to 5.2 lakhs or something. I mean, the amount of money you spend in upgrading the DDR will be much higher. So that is where industry is looking at an alternate solutions, where at an optimal cost, how can we get a performance which is very much on par with the DDR kind of performance. That is where the CXL plays the important role. So let us now move on to the next part of the lecture. Okay. As I said, the industry is hitting the memory wall. So what exactly is the memory wall is? This is what summarizes it. The memory performance is not catching up with the CPU performance. So that is captured in this one. See, what is happening is, with the time, as we are progressing with the time, assume that it is 2010, 2015, 2020 time frame. uh, the performance is increasing, let's say from 10 factor to 60%. I mean, on a per year, performance is increasing 60%. I mean, in previous year, let's say in 2022, you used to get some performance, let's say 10 gigabytes per second transfer, for example, from the core, say, CPU core. In 2023, by increasing the number of cores, see, how do you majorly get the performance improvement is by increasing the number of cores. we are able to achieve 16 gigabytes of per second transfer data rates. That is the 60% per year increasing. Whereas the DDR, the memory performance, is not able to catch up with that. The memory performance is only growing 7% per year. So that means there is a gap of almost 50 to 53% every year. So basically DDR is just not able to catch up with the processor performance improvement. That is where the DDR is becoming the limitation. This is one reason why we need that alternate solution. Next, the next limitation is the one is the limitation with the performance, right? Because the DDR is just not able to work at any speed. As I mean, let's say DDR, if you see, it works at, let's say, 3.2 gigahertz, or let's say maybe 4.4 gigahertz. You cannot just run it at 10 gigahertz. If you run it at 10, automatically this will double. Instead of 7%, it will become 100%. But that running the DDR at 10 gigahertz is not a practical solution, because DDR timing cannot be closed at 10 gigahertz. That is where we are hitting the memory wall. This is the bandwidth wall. We are hitting the performance wall, memory performance wall. Then comes the memory size wall. I mean, memory size limitation with increasing core count. With large number of cores added. For example, the server I am purchasing, it has got 32 cores. It gets difficult for memory bandwidth to keep pace with the CPU core count growth and maintain 4 gigabytes per second core over time. I mean, generally the industry standard is per core you want to maintain 4 gigabytes per core over the time. This is like a benchmark standard. I mean, if you have what is the industry standard is, if you have 32 cores, you should have 128 gigabyte of DDR. That will make it 4 gigabyte of DDR per core. But this is where we are hitting the limit. I mean, cores are increasing significantly, but the amount of DDR that you can connect onto the motherboard gets limited. That is also captured in this one. See, over the years, starting from 2010 till 2023, in 2010 we had a servers, like I'm not talking about the laptops that we are using. I'm talking about the servers chips that Intel and AMD releases. In 2010 they had a CPU architectures with 8 cores. That time the theoretical DDR memory data rate was 10.7 gigabytes per second. Okay, back in 2023, I mean back to 2023, that is forward to 2023, the number of cores have increased 16 times. You can see how much, 8, 10, 12 times, right? Number of cores have increased by factor of 12, but the performance has only gone up by 3.5 times. See, the max theoretical DDR max memory data rate used to get was 10.7 gigabytes per second. Now in 2023, what we are getting is a 38.4 gigabytes per second. You see, that is where we are hitting the limitation with the DDR throughput. And this is one aspect. The second aspect with the amount of memory that you can connect. See, as I said, amount of memory you can connect into the motherboard is limited by the number of channels, memory channels. See, earlier in 2010, we had 2 channels on the motherboard. In 2023, that has been increased to 12. Now you may say, why don't we just keep on increasing? That is at one point really unrealistic, due to probably it could be due to the electrical aspects of the chip, it could be due to the area constraints. It becomes unrealistic. Okay, now you see it again has increased only 6 times. See, basically you see the neither the bandwidth, neither the capacity is able to catch up with the CPU core count. And other than that, the system memory bandwidth, the overall system memory bandwidth, what you have achieved is 460.8 gigabytes per second, which I feel somehow catches up with the overall speed. See, 21.3 is catching up with it. Okay, but see, the limitation remains with the memory size. And if you take overall division, I mean, of the amount of memory that is present per core, in 2010 it used to be 2.7, then it became 4.3. How it became 4.3 is they increased the number of channels. See, wherever they increase the channel, see from 4 to 6, this number has gone up because they are able to connect bigger amount of memory. Again, 6 to 8. This hasn't gone up because here the numbers have again increased. Okay. When it became 8 to 12, this became 3.2 to 4.8. Again, we are expecting CPU core to be 256 count. I mean, one server having 256 cores, CPU cores. Okay. There it again coming below the benchmark number, that is 3.3. So that is where industry is looking for the alternate solution. I hope you have understood the concept of what is meant by memory wall. So how CXL solves the memory wall problem? Currently, the optimal way of implementing system memory is DDR. I mean, if you have to increase your system memory, it is by adding more DDR. For example, in my server, I want to have a better performance. My only way of looking at it is what? Purchase one more DDR and insert it into the empty slot of motherboard. CXL lets user implement any type of memory with CXL interface connected on the CXL interconnect. Understand this statement, very important. The CXL lets user implement any type of memory. It's not just DDR. It could be the flash, any type of memory, but it should have a CXL interface. That memory should have CXL as the interface. That can be connected to the interconnect. Once you are connected, this can be used as a system memory. That could be used as a system memory. It need not be DDR. Next. What are the advantages offered by CXL here is, it uses the PCI Express slots. See, you don't need any dedicated CXL interface. It works on the PCI Express slot, so there is no need of dedicated CXL ports. It works on Gen 6 speed, which gives almost like 128 gigabytes per second at X16. Let's quickly understand how did we come up with this number. Maybe this is little changed. We'll discuss. Gen 6 works at 64 giga transfers per second. We are talking about 16 lanes, and we are talking about two direction, right? Bidirectional. So 64 giga transfers per second, 16 lane into 2. Divide by 8. This will become bits, because 16 bits it will become due to the 16 lanes. Divide by 8 will make it what? 2. 2 into 2, 4. 256 gigabytes per second. This would be not 128. 128 gigabytes in one direction. 256 gigabytes per second in both the directions, bidirectional mode. So that is the maximum throughput you can get out of it. Okay, even though whatever be the device, it could be SSD, it could be any type of device, at the PCI interface level, you are able to get this much bandwidth. This is what CXL uses. The CXL uses the advantage of this number. So for comparison, if you have to compare these numbers, DDR5 6400. I mean, this is one of the generation of DDR5, one of the category of DDR5. Working at IO speed of 3.2. I mean, this 6400 is related to 3.2 gigahertz. It's the double of this number, because it gives since it's a double data rate, this 3.2 essentially becomes 6.4, because you will write and read at both the edges of the clock. That is what they are symbolizing as 6400 transfers per second, mega transfers per second. It offers theoretical maximum bandwidth of 51.2 gigabytes per second. You see, when you use DDR5, you get a theoretical maximum of 51.2 gigabytes per second. Same thing, if I use Gen 6 into the same architecture, I will be able to get 128 gigabytes per second. Assuming we are moving to DDR6, now the bandwidth will double, so we may get 102.4. But if you see, it is still better than that. I mean, see, my CXL is still offering a better bandwidth than what I will get out of DDR6. That is where the CXL is able to give the flexibility of using any type of memory, but still get a performance that is on par with the DDR system memory. This allows for a provision to keep large amount of system memory per core, so that more application can be handled in parallel. You don't need to only rely on the DDR. You can just connect any type of memory and increase the amount of system memory available per core. This is the first part of the thing, first part of the problem that CXL is trying to solve. The second part of the problem is the problem of IT resource efficiency maximization. I mean, how do we efficiently utilize the cloud computing resources? I mean, the servers and the switches, routers, the memories, everything. How do you efficiently utilize? So CXL also tries to solve that problem. In fact, that is one of the very important aspect of the CXL protocol. So what is the problem of IT resource efficiency maximization is, see, workloads have dynamic need for compute horsepower, memory storage, latency, and IO bandwidth. What is mean by that is, what is mean by dynamic need is, I will give you one example. Let's say in the institute, uh, Monday 10 a.m. to 1 p.m. we do physical design training labs. We do functional verification training labs. Okay, we do DFT labs, for example. So what happens? Around 100 plus users are connecting to the cloud, connecting to my server and cloud, and accessing all the applications same time in parallel, right? Applications in parallel, rather. Same thing, Monday 11:30 p.m. there are only 10 plus users because it's midnight, close to midnight. There are only 10 plus users connected to the server. So you can see the difference. It's the same institute, it's the same server, it's the same applications, but there is a very dynamic nature of resource utilization. So at one point, we have to support 100 plus users. At one point, we have to only 10 plus users. Now tell me, when I go to, let's say I go to Amazon Web Services, AWS, and I want to take the hosting service. I want to host my applications on their cloud, applications on AWS cloud. So will I take 100 plus users capacity, or will I use 10 plus users capacity? What is that I'll go with? I have to take into consideration the worst case possibility where 100 plus users connect. But then there is almost a 50% of time I go with 100 plus users utilization. Assumption is that those many users can connect at any random time and they may use. So this is where comes almost a 50% of time my resources are underutilized. One is from my perspective, one is from Amazon perspective. Even from Amazon Web Services, let's say they have reserved 64 cores to my applications. Let's say they have reserved, let's say 256 or some 256 gigabyte DDR and some storage, some SSD storage. Okay, they have reserved so much space. But this is not getting utilized always to the core. It is only 50% of the time a good portion of this is getting utilized. That is where comes how can we make this whole process efficient. One thing that industry has done is, can someone tell me what is being done to solve this problem? What is that one thing that industry has done to solve this problem of efficient utilization of the resources?
Dynamic
The answer,
allocation maybe on a weekly basis or a daily basis, depending upon
that is called as
its.
virtualization. Virtualization is what industry has used. The cloud, I mean, virtualization is a very important concept in the cloud computing. So let us talk about what exactly is this and what exactly is the virtualization. Okay, so as I said, workloads have a dynamic need for compute horsepower. I mean, number of cores required, amount of memory, amount of storage, amount of the latency, IO bandwidth. So now I hope you understand the concept of dynamic need. As the nature and complexity of algorithm changes, the workloads and services are optimized to be delivered over installed unchanging public and private cloud hardware infrastructures. For much of the recent history, industry saw incredibly low overall data center resource utilization. I mean, the companies only use 50% of the resources they invest into. They don't utilize the entire resources at full time because of the varying dynamic variation of the workloads. Uh, to solve this problem, industry uses the concept of virtualization and cloud infrastructure provided. See, cloud infrastructure means what? It's one resource which many people can connect and use. See, let's say I kept my servers in my institute office room. Anyone else use it? No, right? I only we can use it. Whereas if I tell that I will purchase 10 servers, let 20 of us collectively use it, that will become a cloud infrastructure where multiple people are using it. In the same context comes the concept of virtualization also. So the virtualization and cloud infrastructure provide capabilities to help conserve, even reclaim the resources lost to over provisioning. See, like you over provisioned by 50%. Now, due to the virtualization, we could use that underutilized 50% for some other applications which is being used by some other user. So that means what? The same hardware, same memory could be allocated for different applications in a shared manner. Virtualization, you have the same hardware but multiple applications running concurrently on that. Basically, whatever is lost to the over provisioning and underutilization through enhanced automation. It doesn't happen automatically. It needs to be done through some enhanced automation, workload migration, and placement, and other techniques. They use some techniques to implement the concept of virtualization. So, what exactly is virtualization? See, virtualization is, this diagram summarizes the virtualization. Please go through it once. You have the server hardware. On that you have host operating system. Then you have hypervisor. See, hypervisor is one of the uh, concepts related to the processor instruction set architecture. I mean, processor programming model, where that allows multiple uh, guest OS to run concurrently. See, this hypervisor will allow these three things. You see this one, each of them has their own guest OS, binary libraries, and applications, all of them to run on the same hardware, as if they will think. See, this will think that I am the only one which is using these resources. This will think that I am the only one which is using these resources. So the hypervisor gives that kind of feeling to all these applications. So this concept is called as virtualization, where the same hardware is shared by means of hypervisor to various applications in parallel. So virtualization is a process of creating virtual version of something like computer hardware. So you are creating virtual version. What is meant by virtual version? You are not cutting this into three hardwares. It's the same hardware, but in a virtual manner you are sharing it. With the help of virtualization, multiple operating systems and applications can run on the same machine. They can run on the same machine and its same hardware at the same time. So they can run on the same hardware at the same time by increasing the utilization and flexibility of the hardware. It increases the utilization because you're able to utilize the hardware very efficiently, because you're able to concurrently run different applications. It is one of the cost effective hardware reducing techniques used in the cloud computing. I mean, if all this AWS works, Google Cloud Services or anything works, it is all because of the virtualization. That is where they are able to cut down the cost. Let's say they are charging me 4 lakhs, okay, for cloud hosting of my application. They don't uh, allocate all resources just to me. They share their resources by means of virtualization, so that they don't have to invest all 4 lakhs just to purchase the hardware specific to my requirement. They utilize everything in such a manner that by means of virtualization they are able to utilize their resources efficiently. That's the summary. Okay. Okay, next, virtualization allows sharing of single physical interface of resource or applications among multiple customers and organizations at same time. See, what does virtualization do? It allows sharing of the single physical instance of resource. It could be the hardware, it could be the memory, or application among multiple customers and organization at one time. Yeah, Sivanshu, what is your doubt?
Yeah. So when we say the virtualization, like how are we sharing the resources? Is it time multiplexed, or like do we have multiple execution pipelines that are being utilized? Like how is it
I
being
believe
used?
it should be multiple execution pipelines because there are multiple cores. The hypervisor is responsible for scheduling those things.
Okay, I see.
Okay. Maybe we can talk more about what else is involved. It could also involve time division multiplexing, but I would assume, see, since they say it allows sharing resources where all things are can be running parallel. This allows for multiple applications to run parallel. It won't say that one application would stop, other application would run. It would optimally utilize my hardware where it will divide part of resources to one application, part of resources to other application, part of it to other application. Let's say I have got, for example, 32 cores. If this is the only application running, it may allocate all 32 resources to me. If there are two things running, it may divide this 32 resources into two parts into each of us. I believe that is what should be the essence of the virtualization.
Okay. Does that mean the number of execute pipelines that you have should be equal to the? So I mean, it means that there is a bound on the maximum number of concurrent processes you can have over your server, right?
Yes, of course it will increase because you cannot see there is a limit, right? If you are running three applications and you have only one hardware, you will not get the same performance as having three different hardwares running three different applications. The assumption here is what? All people don't use the applications at the same time. I mean, they will have varying. See, someone may be utilizing in this manner, some other company may be utilizing in this order, some other company may be using in a little different order, for example. So they are adding up all the resources here. They keep this as the limit. I believe this is what summarizes what exactly is the virtualization. I will check over it. I mean, whether time division multiplexing also is involved into it, and I will get back to you.
Okay. Okay.
One we have
Thank you.
discussed is the resource sharing. The second thing we are talking about is there any time division multiplexing involved? That also we'll discuss. Okay.
So, Srinivas, one question regarding resource sharing. Is there
Yeah.
any particular cap or a threshold on an individual application in that case?
I think that is what virtualization does. See, if you see the previous slide, it tells that in virtualization, they do automation, enhanced automation, workload migration, placement of the resources, and other techniques. This, even though these are very short words, that is a very big thing in when we talk about virtualization. They will allocate how much resource and all that according to these factors.
Thank you.
So we have discussed all this. Okay. Next, I think another 5 minutes. We'll go for a break. Okay. So evolution of the CXL architected data center. See, CXL will change how traditional rack and stack architecture of the server and fabric switches are deployed in the data center. See, typically what happens right now, you will see that when you think of a server, see, when I think of a server which is present in my institute, you know what I do think of? I think of a uh, some CPU core, CPU processor with multiple cores. It could be 16 or 32 cores. I will imagine some RAM which is connected into my motherboard, and I can imagine some GPU or some accelerator which is connected onto my motherboard. That is what I can think of. I will think of that whole thing as one unit. So if I have to increase my resources, I will think of how many such resources I can multiply. That is what I would think of. So cores, RAM, accelerator, and SSD. Again, cores, RAM, accelerator, and SSD. That is how I would multiply. What CXL does is it kind of changes everything. Eventually, going forward, what will happen is in CXL later generations, they will give a provision where all CPUs could be just connected as one at one part of the node. All memory, system memory could be connected as a different set of node. All accelerator could be separate. So that way you can just do whatever way you want to utilize the resources. Let's say you want a large number of CPU cores, you want some amount of DDR, some amount of accelerator. That will give you provision to use a set up a infrastructure, cloud infrastructure, only by selecting those things only. You will not be restricted to this approach where you have to create a server with this kind of combination. you can just select whatever way you want. Okay.
I have a question
Servers
here.
in the rack.
So
Yeah.
yeah, so in the future possibility that you showed for the CXL,
Yeah.
does that mean for the each processor, will it be like a single root port, or will it be like, I mean, you cannot have a single root port for all the processors, right? It should be separate, right? So you're basically essentially saying like you will have multiple CXL ports for each of them or each of these processors, but classed as one, is it? Or like how are you
No, 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 no.
saying this?
Each device will have only one port only, one PCI port. All of these are connected into the CXL interconnect, onto the CXL interconnect.
Okay.
I think I have some diagrams as we go forward that will help you understand in more depth the same concept. Okay. So let's wait for a few more slides. We'll talk about that also. Okay. So servers in the rack, once interconnected to fixed resources for network and storage and compute to function as a solution, will be dynamically composed. See, this dynamic composition is the very important thing. In what is dynamic composition is ability to select how many cores I want, how much amount of RAM I want, how much amount of SSD storage I want. That is what CXL will give me the provision to use that through software management infrastructure to meet the demands of modern emerging workloads such as AI and deep learning. Okay. So this is what is we are talking about. See, this is the existing style. This is what is currently happening. This is what we are expecting in future to happen. Future means another 1 year, 2 years down the lane, probably. Okay. So you see right now what is happening is there are switches. Okay. And then you have got cores. Black ones are the cores. Then you have got the IO and storage. This is the IO and IO storage, and this is the system memory. Okay, this is how you think of. This is like one my server box. Cores, IO and memories, SSD and all that. Then the DDR system memory. Same thing. I think of my existing infrastructure like this. With emergence of CXL, this will change to this one, where you have got TD switches connecting to the various servers through directly in this manner. These servers, this is not CXL. Understand, this is not a CXL technology. This whatever blue color you see here in this diagram, whatever blue thing you see here is the one which is connected through the CXL technology. So IO devices, accelerators, and the system memory. I would that is part of the servers, and then you have got CXL appliances like system memory and the IO. These are the expander pooling expander. These are can be used for expander purpose, pooling purpose, accelerator purpose. They are interconnected through the this line. What you see is the CXL interconnect. So this will give provision for this applications which are running these to use these resources and also to select some of these resources which is present on the interconnect. So this is what is emerging right now. In the future, the goal would be to change this to a mechanism where your memories are separately kept as a one bunch of units. IO and storage becomes one more thing, cores becomes one more thing. Core could be computing or acceleration. Now you could select this many cores I want, this much memory I want, this many IO and storage I want. That will become one of the unit. Okay, one of the server unit. This is what we are provisioning. I mean, we are looking for in the near future. Okay, this is what CXL is going to do basically. That is why the CXL is the next big thing that we are looking at.
So, Srinivas, one quick question here. As you
Yeah.
mentioned, resource pooling, or basically, so will each application broadcast its required memory requirement or resource requirement, and that will be captured by maybe CXL driver software in some way?
Yes, yes, yes. See, CXL, when we say CXL, it's not just the hardware. See, anytime you talk about PCI Express, PCI Express is not just the hardware. PCI Express
Okay,
is the drivers that are running on the PCI hardware also. So,
right.
not everything will be done by hardware only. how many resources to take, how many cores to take, which core should run which application, which memory should be pulled in, which IO and storage should be pulled in, that will be decided at the driver level.
Okay, sure. Thank you.
Next question: how CXL addresses the hardware challenges? What is the challenges in current hardware is, and first is challenges and how CXL addresses these challenges is, current challenges is what industry trends driving demand for faster data processing and next generation data center performance. That is what is industry is driving for. Increasing demand for heterogeneous computing and server disaggregation. What is mean by that? Having different types of cores, different cores coming from a different vendors, that's all becomes heterogeneous computing and server disaggregation. Need for increased memory capacity and the bandwidth. So CXL addresses these challenges by creating an open industry supported cache coherent interconnect. This is very important for processors, memory expansion and accelerators. It creates a coherent interface, leverages PCI Express with three mix and match protocols, and it creates a low latency dot cache and dot memory semantics targeted at near CPU cache latency. It also creates something called as asymmetric complexity. It eases the burden of cache coherent interface designs. Okay, so this is a very brief about how CXL addresses